Hello, this is Mr. White, and this video is on inverse trigonometric functions. Now, if your first thought is, inverse, isn't that the same thing as reciprocal? Well, maybe in a previous math class in some other context that you were told that was true. But in this context, when we talk about inverse trig functions, we are not talking about reciprocals. Now, before I tell you what inverse trig functions are, let's start with a quick review of some things that you know, but maybe some connections that aren't as strong as they need to be. You know that if you have an angle such as 5 pi over 6, that's a unit circle problem. You should be getting pretty comfortable with those by now. You should know that that is equal to 1/2, and that the 5 pi over 6 is a shallow special triangle in the second quadrant, and that the 1/2, here's the 5 pi over 6, and that the 1/2 represents the opposite over hypotenuse ratio. Okay, but when you look at the bottom one, this is where I find that students typically at this point in the course start to get a little bit shaky or tend to lose focus as to what they're dealing with. Let me actually point out that if you were to type, going back to that original equation, if you were to type 5 pi over 6 into your calculator, you would find that as a decimal, it's about 2.6. Obviously a little bit more, as you see here. But now when we look at those two equations and we say, oh, really, 5 pi over 6 as a decimal is pretty close to this value, it shouldn't surprise us that the 1/2, or 0.5, is pretty close to this value. But again, I find that a lot of times students, as soon as they pick up the calculator, they kind of lose focus and forget that that 2.6 is an angle in radian measure, and forget that that 0.5155 might be helpful to think of it as being over 1, where you can really just affirm for yourself that, oh yeah, that represents a ratio of opposite to hypotenuse on the unit circle. Okay, so again, reminder, when you pick up the calculator, don't turn off your brain. Remind yourself whether you're dealing with angles or ratios or whatever. All right, so let's change the question a little bit. What if I know the ratio and now want to know the angle? Find out the angle. Well, I'd ask you, what do you think is underneath this question mark? Sine of some angle equals √3 over 2. Well, if you're pretty good, you're probably thinking √3 over 2. All right, not bad. However, if you're really good, you'll be thinking, well, there's an infinite number of possible solutions. Think about it. Unlike this, let me go back to the previous slide. Unlike this previous slide where sine of the angle 5 pi over 6 can only equal 1/2, and I could write it in a different form. I could write 0.5, but it's still equal to 1/2. However, there are infinitely many distinctly different angles that could be underneath this question mark. I'll remind you that the obvious, or relatively obvious answer of pi over 3 represents this angle here, pi over 3. But we could also get to that same part, that same angle on the that same triangle on the unit circle by going -5 pi over 3, right? Or we could go in the positive direction but go around more than once and get 7 pi over 3. There are infinitely many coterminal angles. And furthermore, I don't even have to deal just with that one quadrant. I can deal with angles in the second quadrant because those also have positive signs. I can deal with my 2 pi over 3 or my -4 pi over 3 or 8 pi over 3, etc. Infinitely many possibilities that could be underneath this question mark. And same deal when we're dealing with a non-special angle. So even though you look at that 0.9 and you recognize that's not any of our special trig ratios, you actually know how to solve that, believe it or not. You already have the tools to solve that. If you think of that question mark as being x, hopefully you're going, oh yeah, sine of x equals 0.9, I know how to solve that. You grab the calculator, you do y1 equals sine of x, y2 equals 0.9, and you get something that looks like this, right? And you see 6 intersection points on the screen, but you know there are really infinitely many if we're able to extend our window settings infinitely. And if I just take those 6 intersection points that we see on the screen right now, and I provide their x values here, I just need to remind you again that don't just look at it as some number, think of these as angles in radian measure on the unit circle. That's what I'm trying to affirm for you here. And if you were to take that -5.163 radian, which ends up being in the first quadrant, And if you were to add 5 or 2 pi to it, you would get 1.12, also in the first quadrant. If you add another 2 pi and get another full trip around the unit circle, another coterminal angle is 7.403, etc. And all these angles right here represent these intersection points on the sine wave. Likewise, these other angles here are also all coterminal, and they represent these other points here. So again, haven't really shown you anything brand new yet, but I'm just affirming things and reminding you of connections you need to be making all the time. Alright, so it turns out inverse trig functions are an alternate way of finding an angle when you are given a ratio. And like many times in math where you have multiple methods of doing something, it's got its pros, it's got its cons. I'd say one of the good things about it is it's quicker than graphing. It's also more flexible. Any scientific calculator can deal with inverse trig functions, whereas you specifically need a graphing calculator to be able to solve graphically. There are many computer programs out there that can deal with inverse trig functions, yet don't have any sort of graphical solving capabilities. I'd say the major disadvantage of inverse trig functions is that they are indeed functions, which means they can only give you one output. So if I go back to the previous slide, with graphical methods I could find as many of those infinitely many solutions as I want. We're going to find that with inverse trig it really just gives you one solution, and you have to figure out how to deal with that if you decide to go the inverse trig route. So let me show you what this looks like. On the left here you see a regular trig equation, and as you know, with sine, cosine, tangent, you plug in an angle, you get a ratio in return. However, with inverse trig, as you see on the right here, you plug in a ratio and it gives you the angle in return. Now what's probably catching your attention right now is this notation, which looks like an exponent of -1, but I have to tell you right now, please don't say sine to the -1 power. That is not what this is. How do you say this out loud? Well, again, you say inverse sine of √3/2, and again, it is not an exponent. This is an unfortunate notation in my opinion, because it's so easy, it looks so much like an exponent, but it is not. Because of that really easy opportunity for confusion, a lot of people prefer this alternate notation, arc sine. So you can either say inverse sine of √3/2, or you can say arc sine of √3/2, and they mean exactly the same thing. There's not a difference at all. You should just be able to be comfortable with it, whichever format I give you, whichever notation I use on a test or you may encounter in a textbook, they both mean the same thing. Alright, so this next slide just really affirms that point. I just find myself explaining this over and over again every year, and just for added emphasis, let's make this really clear. These are not the same thing. Let me go over to the one on the right here. This one on the right, that is sine of x to the -1 power. That is what is equal to 1 over sine of x, the reciprocal of sine. And as you already know, that is what is equal to cosecant of x. So all of these are the same thing, very different from this over here. And as you notice from the color coding too, the x over here, when you're doing inverse trig, the x represents the ratio. You plug it into inverse sine and you get an angle as an output. Whereas with our familiar regular trig, you plug an angle into sine and you get the ratio as an output. So make sure you're clear on that distinction. Alright, so if there are infinitely many angles that share the same trig ratio, if there are infinitely many solutions, how do I know which one the inverse trig function is going to give me? Well, let's clear that up right now. When you're dealing with inverse sine, you will always get an angle that is somewhere between -pi/2 and pi/2. So if you envision that on the unit circle, -pi/2 all the way up to pi/2, that means you're always going to get an angle in the fourth or first quadrant, no exceptions. Inverse cosine will always give you an angle between 0 and pi inclusive. So you will always get an angle somewhere in the first or second quadrant, possibly those quadrantal angles at the end, but you'll never get an angle in the third or fourth quadrant. Now, if you're thinking, do I just have to memorize this? To some degree, yes, but there is a certain logic to it, and we'll wait till class to discuss the logic to it, but I'll invite you to start thinking of it on your own. See if you can figure out why these limits are set the way they are, why these intervals are set the way they are. Notice that inverse tangent has the same range as inverse sine. You will land in the fourth or first quadrant, not the second or third. Let me show you a different representation of the same information. If we look at the sinusoids and the tangent curve as well, and we look at where those intervals lie, we know that the spacing on the basic sine wave is such that this is negative pi over 2, this is positive pi over 2. So the inverse sine will give you an angle somewhere along this stretch of curve. Let me point out that if you were to graph y equals inverse sine of x, you would get something different than what I have on the right here is just the plain old y equals sine of x. I'll invite you, if you're interested, to explore what this graph looks like on your own. We'll save that for class though officially. Inverse cosine. On the basic cosine graph will represent this stretch of angles, inverse sine, this stretch of angles. So again, I just ask you to reaffirm in your mind that the angles are along the horizontal axis on these trig curves here, and that the inverse trig functions represent these indicated regions of those curves. Alright, let's do an actual example. Now that I've spent a lot of time on the concept and the connections I want you to be making, I'm going to go fairly quickly through the actual example because I hope you'll find that the mechanics of this are pretty easy once you got the concept down. Inverse cosine, we said that will not land us in either of these two quadrants, and given that I have a negative sign there, I know that cosine could only be negative in this quadrant. Not my best drawing, but I'm going to run with it here. Negative 1 over root 2, I remind myself that's the ratio that I'm dealing with here, and I know that from my unit circle knowledge that is equal to 3 pi over 4, and guess what? That is my final answer, just like that. Alright, I hope you're following along. I hope I didn't go too quickly there. Let's go on to a little more complicated looking one, but we're going to find it's not that bad. This looks a little intimidating at first, but I would urge you to just remember that you know how to handle nested parentheses. You know that you work from the inside out. So ignore the arctan there for a moment and just focus on tangent of 5 pi over 4. That we've been working on long enough where I'm not even going to draw a picture. I'm going to trust that you know that that is in the third quadrant, that angle is in the third quadrant, and its opposite over adjacent is negative 1 over negative 1, or just 1. Now when I allow myself to focus on the arctan portion of that, now I say, what is the arctangent of 1? What is, and I remind myself that in the first, or that inverse tangent or arctangent will land me in either the fourth or first quadrants, and since I'm dealing with the positive value, I'll be dealing with the first quadrant. Again, fourth quadrant would give me positive 1 here and a negative 1 here. It's the first quadrant that gives me a 1 over 1 tangent, so I'm interested in this angle of pi over 4. And that is my final answer. I should have drawn that a little bigger since it's my final answer, but I'll put a circle around it. That's it. I hope I don't go too quickly there. As always, come on by to office hours if there's anything in this video that is not clear. Let me just point out real quickly that for time's sake, to keep this video from getting too long, I'm going to save calculator examples for class, but I bet you could pause this, and if you do and you evaluate this in a calculator, I just urge you to remind yourselves what those numbers mean that pop up on your calculator. Alright, time for you to try. You know the drill. Pause the video and we'll see how it goes. Alright, let's see what the solutions are to these exercises. There you have it. I hope you found that this all made sense, and I'll see you during office hours if there's anything that you have questions on.